All right. Okay, so I saw a couple things on the Campus Wire, and some questions. So one was like when I type in Jupyter Notebook, it starts in whatever folder. So the normal way around this is you type in like CD, and then you change into the directory that you want. So I use OneDrive, so I'll do like CD OneDrive, CD Teaching, CD 131. Okay. However, there's another option, and in your depending on your computer. So on a PC, under users, I don't want that. There's going to be a folder called .jupyter, and inside there is a configuration script, and you can edit this configuration script, and everything is commented out. Okay, but you're going to search for one of these things. On my thing, it's like around line 213, and you're going to uncomment the thing that says notebook app, notebook directory, and you can specify the folder where it starts up. Okay, and so for here, I specify my 131 folder, and that's what I have. And I think it'll be in a similar location if you're on a Mac user. You kind of inside your user configurations, there should be a .jupyter folder. You might have to use ls to kind of show the folders. Folders that start with a dot are generally hidden, and so you might have to have that revealed. But that's an option. Okay. And then when you start up Jupyter, and again, I'm always kind of a fan of using Anaconda prompt. You type in Jupyter Notebook, and that will start, run a server on your local machine called the localhost server, and then it will open up this thing in your browser. And so Jupyter is always, you kind of interact with Jupyter via the browser, and that's where we are. And so today we'll take a look at this notebook called More Numpy, and we'll look at more Numpy stuff. And I posted the homework. The homework, I've decided to try to avoid any kind of issues that you might have with GitHub. So again, I'm still a big proponent of GitHub, and I think it's kind of the best way to get the notes, which is where I'm posting everything. All you have to do is kind of do a git fetch upstream, and then git merge upstream master, and it will pull down my notes and put it into your repository. But as far as the homework, I just uploaded it to CCLE. You'll download the notebook, put in write up your scripts, and render everything. What you'll want to do is, after you write everything, you're going to want to do restart and run all. And this will kind of go through the notebook and run through everything, and then go through after you do a restart and run all. So I'm just doing it on this one. If you've done everything correctly, it should get to the end without any kind of errors and stuff. And you'll want to just kind of take some time to go through and make sure everything did indeed run correctly. Looks like, okay, we're running. Seems like my computer's struggling a little bit. Okay, I'm gonna have to figure out what's going on here. But I'm gonna go ahead and just do a restart and clear. But you'll do a restart and run all, and then at the end, make sure you do file download as HTML, okay? Because as you know, if you try to just open the notebook directly, it looks funny. Okay, you've got to kind of start up Jupyter and then you have to open it that way, and I don't want to have to make the graders go through that process for every single person. So just download it as a static HTML thing, upload that, and then the graders will grade through your answers and responses. Okay. I don't know if you guys took a look at the homework already, and if there's any questions. The first few questions should be fairly simple, like just maybe like 2 lines, and then the last 2, will be a handful of lines, but it shouldn't be anything too crazy or too complex. Okay. Okay, so we'll talk Numpy today. So Numpy again is the way Python will handle matrices, or just in general arrays, where everything is going to be of the same type, generally numbers, either floats or integers, and you can everything's called an ND array, for an n-dimensional array. And we look at the shape and all of this stuff. So anyway, a quick way is we can do a range for make an array with a range. And so if I do 0, 4, 1, what will this produce? 0, 1, 2, 3, right? It ends at 3. Okay. And and then y will go 100, 101, 102, 103 if I do 100, 104, 1. Okay. The comma 1s are a little bit redundant. It defaults to doing comma 1, but I'm just kind of fully specifying everything. Okay, so you can kind of join these things, okay? And if you do concatenate, it sticks them end to end, okay? So it just kind of joins these. It's kind of like the C. In R, you have C to combine vectors, and similarly, we have this, okay? But concatenate's a little bit more general, and so by default, you can do axis 0, which will go kind of on the 0 index, okay? And then axis 1 here, this will actually throw an error. So on the 0 indexes, so basically, what is the shape? Let's ask this question first. What is the shape of x? If I said x.shape, what will it print out? It'll be what? It'll be 4 comma, okay? Because it's only one-dimensional, so there's only one dimension here, okay? It's not a 4 by 1 or a 1 by 4 matrix. It's an array where there's only one dimension, okay? So it's going to say 4. And so if we say, if we look at this object here, and I ask, what is the index of 4? You would tell me it's index 0, right? So I can concatenate along index 0, and there's no value at index 1, okay? There's no value at index 1, so I'm not able to concatenate along axis equals 1, right? I can use something like vstack, okay? And this will stack the array 0, 1, 2, 3 on top of the array 100, 101, 102, 103, okay? But let me just kind of just show you kind of how these concatenate things work, okay? So here I'm going to take a range 0 through 6, comma 0, 6, 1. So this is 0 through 5. 0, 1, 2, 3, 4, 5, 6. Okay. It says 2 rows, 3 columns. And then I do the same thing with 100, 106, 2 rows and 3 columns. So the range creates a one-dimensional array, and then we run reshape to kind of reshape it into a 2 by 3 array. And I do this the same for the values 0 through 5 and 100 through 105. Okay, so I've got x as a matrix, x matrix, and the y matrix right here. Okay, so if I concatenate these two, it defaults to concatenating them along axis 0. Okay, here I can call concatenate on axis 0, and it returns the same thing. Okay, so just to kind of show you what's happening, if I say xm shape, okay, the dimensions are 2, 3, right? 2 rows, 3 columns, and so by default, concatenate will concatenate along the first listed dimension, which will be axis, kind of the axis equals 0. We'll say concatenate this dimension 2, okay? And if I say ym.shape, it's going to stick the 2 on top of the 2 so that you will get a 4 by 3. Okay, that's what concatenate by default, or concatenate axis 0 is doing. Does that make sense? And so when I say concatenate on axis 1, it's going to take the 3 and the 3 and add those together. So you're going to end up getting a 2 by 6. All right. And so here we get a 2 by 6. Right. So I want to make sure that it makes sense to the way this concatenate thing is working. Okay, it's going to kind of join by default. It joins on the axis index 0, or the shape index 0. So when we say axis 0, it's going to add the 2 and the 2, and it's going to end up having 4 rows, and it's going to leave these intact. So it'll be 4 rows and 3 columns. And when I say axis equals 1, it's looking at index 1, which is the 3, and it's taking the 3 and the 3, adds those together, so it's going to end up being 2 by 6. Okay, so get used to seeing 0 indexed things. So axis 0 is kind of by rows. Axis 1 will be by columns. Okay. And then again, if you have a higher dimensional array, like a 3-dimensional array, you can say axis equal to 2, and it will concatenate based on the that 3rd dimension. Okay, and so that's why over here, when I had just kind of this 1-dimensional vector, okay, I can only concatenate with axis 0. Okay, because x's shape has only 1 dimension. There's only a 0. The shape has only an index 0, and you can only concatenate that. So if I take x shape is 4 and y shape is 4, when I concatenate it, it's going to be it's going to have a shape of 8, comma, and that's why I have this. And I cannot call axis equals 1. Okay. If I wanted to stick them on top of each other, I either have to reshape it so that it has 2 dimensions, or I can use this v stack, okay, where you stack x vertically on top of the y. So you can do that. Okay, so v stack will basically do concatenate, in our case axis 0, and h stack will do concatenate in the horizontal way as well. So these are kind of some options that we have as well. Right, so these are kind of, in R you have C bind and R bind and things like that, and we have this. Okay, we have concatenate, and I probably I don't know. Do I use concatenate or VStack or HStack more? I probably use concatenate a little bit more. Just you kind of get used to your vocabulary, and you use the same functions over and over. But you know, these things are handy as well. Okay, so let me just kind of print out x, y, xm, and ym. Okay, so all of these things, you know, after they stack them, return kind of new things, and they don't actually modify the originals. So we have x's, these are one-dimensional, and then xm and ym, we can tell that they are two-dimensional, again, because they have double two square brackets. Okay, so when they open and close, you can kind of see how many dimensions you have, because you kind of have two square brackets in a row. And over here, I only have one square bracket, indicating that it's only one-dimensional. Okay, so you can do math stuff like x plus 5, and you just add 5 to every number in there, x plus y, and then you're adding them element wise. Okay, and you can do element wise addition, you know, and the 5 gets they call it broadcast. R calls it recycling, but in Python it's called broadcasting. So the 5 gets broadcast to, you know, every element in this array, and when I do xm plus ym, it's going to do element-wise addition and add them up accordingly. Okay. The dot will do a dot product between x and y. Okay, so you're basically taking you know, the vector x, and then you're doing a dot product with the vector y, and so you'll get a single value. Okay, so the vector x is 0, 1, 2, 3, and vector y is 100, 101, 102, 103. So you're going to get 0 times 100, 1 times 101, 2 times 102, and 3 times 103. And when you add them up, you get 614. Okay. And then and you can do element-wise multiplication. Okay, and element-wise, you know, for vectors, you know, for one-dimensional arrays and two-dimensional arrays, and you know, higher dimensional arrays, as long as the dimensions line up. Okay, so these element-wise operations, I think they operate as we would expect here. Okay. You have more just kind of regular old math functions. Okay, so again, you can just do a range 4 and it'll produce 0, 1, 2, 3, and then all of these things. These are just regular old math things. I don't think any of these are surprising. The power is 2 stars, okay, rather than a caret. If you do like the caret operator, it's going to kick back an error. Okay, and then percent is modulo, so that's going to give you the remainder, and then you also have the absolute value function for all of this. Okay, so these are just kind of your standard math operators. Okay, you have trig functions. Okay, but they do not exist in base Python. You either have to import math, or they're part of Numpy, and so you can import. When you import Numpy and you want to use the sign function, you can use np.sign, okay, because the sign function exists under Numpy. Okay, so here I'm doing linear space from 0 to pi by 5, so that's going to go 0, you know, 1/4 pi, 1/2 pi, 3/4 pi, and 4/4 pi. So we got 5 elements going from 0 to pi. Okay. So, you know, a quarter, half, 3/4, and pi. And then so, you know, when we do, if we ask the sign of this, we're going to get 0, √2, 1, you know, √2, and pretty much 0. Okay. Again, floating point precision. And then with cosine, you get, you know, 1, root 2, 0, negative root 2, and negative 1. And then the theta will give you 0, 1. This is almost infinity, but not quite. Okay, just a big number, not quite infinity. I guess it's far short of infinity. And negative 1, and then a big negative number. Okay, and then you got your log and exp. So like most languages, log is always going to be the natural log. And then if you want the common log, you have to specify log 10, log base 10. All right. So if we do it on 1, 10, and 100, it'll do this. Okay. And again, if you kind of want these vectorized or array-like arithmetic, you've got to create an array. If I just create a list, well, I don't know, maybe NumPy will. Okay, NumPy is smart enough, and it'll coerce, or it'll convert the list to an array. But if I throw this in there, then we get an error. Okay, so a list will allow different types, but an array will not. Okay. And so here is, to the 0, e to the 1, and e squared. And you can do, so the exp will be e to this. exp2 will be 2 to the y. Okay. And then you can use power, and this will do, whatever value you want. So 3 to the 0, 3 to the 1, and 3 squared. So. Okay, so these are just kind of your regular old math functions. I think we're used to seeing stuff like this. Okay, you have so Python has a regular old sum function, which works. Okay, so if you did maybe. I should, oops. We'll print x first. Okay, so x is the numbers 0 through 99, and you can just say add them up. And then you also have NumPy has a sum function, and it also adds them up. Okay, the NumPy version of sum is much faster. Okay, and the reason for that is because NumPy will know that every value in the array is of the same data type, and so it has kind of some optimized things to handle all of that. Whereas the regular old Python sum thing will accept lists of different numeric types, like a mix of integers and floats, and it's not as efficient. And so here's there's a function called timeIt. It's considered like a magic function. You call %timeIt, and what it will do is it will do whatever operation you have here. Okay. So, and then it does it like, I don't know, 1,000 times, and it measures how long it takes to do these operations, and it will tell you, report back how long it took. So here I'm creating a big array using just some random numbers from 10,000 random numbers. And then I'd say, add up the 10,000 random numbers, and we'll just see. So it's going to take some time to run, all right? And so okay, so here the first operation took 1.76 milliseconds with plus or minus 518 microseconds per loop, okay? And then the other one took 11.2 microseconds. So it's like like 2 orders of magnitude faster, okay? So this is like 1/100th the speed of the, takes 1/100th of the time. So this is on milliseconds and this is on microseconds. So that's pretty impressive that NumPy is that much faster, and it did, over here it only did 100 loops each, and this one it did 100,000 loops each. I don't know, this seems a little overkill, but I'm not the one who does time it. So anyway, you have that. You can do min and max, and it will find the smallest and largest numbers. Okay, and so when you ask for random normal and you ask for 10,000 numbers, it gives you 0.0001 and 0.000998, whatever, something pretty good. And again, the NumPy version of min, you have NP min versus regular old min. If we do time it, once again, we're going to find out that the NumPy version is way faster. Okay, so again, we're on taking about 1 millisecond, and here we're taking 15 microseconds. So it's pretty good, right? Okay. We have, if you want to take a matrix and you want to do operations on it, okay? So here I'm doing random seed, okay? And then here I just take, so one, we can do random and do this, but here I just said take the digits 0 through 11, or not the digits, the numbers 0 through 11. That's what arange does, okay? And then I call shuffle. Shuffle will just shuffle up the values, and then I rearrange them to be a 3x4 matrix, okay? So there I go. The sum function will just take all of these and do column-wise addition, okay? So the default sum function does adds them up by column, whereas the NumPy sum function will take the entire matrix and add them up, okay? Which I think is what I would normally expect. So when I call sum on a matrix, I would normally expect it to just add all 12 numbers together, and that's what it does. But just like before, you can specify an axis. Okay, so if I specify an axis equals 0, how is this going to do the summation? Okay, so it's saying sum over axis 0. So again, the shape here is 3 rows, 4 columns. So when I do axis equals 0, it's going to shape over, it's going to sum over axis 0. It's going to sum over the rows, so we're going to get an array of 4. Okay? If I specify axis equals 1, it sums over the columns, okay, over the second thing, and it's going to give us row sums. Okay? So 1 plus 6 plus 7 adds up to 14. 11 plus 9 plus 8 plus 5 adds up to 13. Okay? And what is the shape? What is the shape of this thing? If I say axis equals 0 sum, what is the shape of this? It's going to be 4 comma. Okay? It's one-dimensional, 4 comma. And then this is one-dimensional. The shape is 3 comma. Okay? And likewise, I can do min, and you can specify the axis, and it will find column minimums. Okay, what's the smallest value in this column? 1. What's the smallest value in this column? 3. What's the smallest value in this column? 4. What's the smallest value in this column? 5. And it does that. Okay. And similarly, you can say I want the standard deviation of the whole matrix, or I want the standard deviation over columns, things like that. Okay. So. Standard deviation over the rows, which will give you column standard deviations. Okay, axis equals 0. So you can, so pretty much all of these summary functions, and you've got, min, max, sum, standard deviation, things like that. You can, most of these you can specify an axis to operate over the matrix. Okay, so we have not a number, nan, and this is kind of how Numpy handles missing values. In R, we specifically had NAs. Python doesn't have that, okay? Python does not have NA, and so if you want a missing value, you need to throw in, you need to turn it into floats, okay? So like R had a NA type for integers and an NA for a type double and things like that. Python doesn't have that. You just have to create a nan float, okay? And if you ask what is x, it's going to come out nan. But if you ask what is its type, it's going to say it's a float. Okay. You'll get nans if you do stuff like infinity divided by infinity or infinity minus infinity. Those will result in nans. And again, if you want to specify infinity, you take the string nan or string infinity. I'm sorry. If you want infinities, take the string inf and you throw it into the function float, and that will convert the string inf into floating type float infinity. Okay. All right. And so if I say sum nan and 2, so if I take x's nan and 2, if I give it a list with these two elements and I say what is the sum of these things, it's going to say it's not a number. All right. But you can also specify nan sum, which says, sum these things up so it can handle missing values. Okay, so this is going to return 2. Okay, so it's kind of like in R you had the option na.rm is true to kind of ignore these things, because if you have an na and you say what's the sum of the thing, it's going to return na, or what's the mean of these things with na, it's going to return na. We have something similar, and so here's kind of the pretty much it's everything that you're expecting, right? So you've got sum, product, mean, standard deviation, var, min, max, and all of these things. And if you want the one that can handle or just ignore nans, it's nan sum, nan prod, nan mean, nan standard, std, and whatever. Okay, so you've got all of that, so those functions work. All right, broadcasting. This is an important concept in Python. It's similar to the idea that in R they recycle values. Like if you give it a vector and you give it one number, it's going to recycle that number over and over, and things like that. It doesn't recycle in the same way that R does. So in R you could give it like one vector of length 4 and another vector of length like 3, and it will like just do its best and kick back a warning. Python says no. Okay, so here A is 1, 2, 3 and B is 4, 5, 6. These are NumPy arrays. When you add them together, it does it element wise and you get 5, 7, 9. So no surprise there. If you try to add 7 and 8 to say 1, 2, 3, Python says I can't do this. Okay, it says A has a shape of 3 comma and C has a shape of 2 comma. Okay, I can't add these things together. Okay. Here I've got A, which is 1, 2, 3, and E, which is a 3 by 3 matrix of 1s. Okay, and so here I can do E plus A. All right, and so E has shape 3 by 3, and A has shape 3 comma, and so what it does is it's going to broadcast. Basically, it's going to recycle, but it calls it broadcast. It's going to broadcast 1, 2, 3 across the different rows. Okay, so you're going to get 2, 3, 4, 2, 3, 4, 2, 3, 4, because it's doing the ones 1, 1, 1 plus 1, 2, 3 for the first row, plus 1, 2, 3 for the second row, and plus 1, 2, 3 for the third row. So it broadcasts these things that way. Okay. If I were to reshape A to be 3 by 1, and if I take E, the ones this way, and I add the column array, the 3 by 1 array now, it's going to broadcast it the other way. Okay, and so we'll get down the columns. Or across the rows, it'll go 2, 2, 2 because it broadcasts the 1, and then we'll get 3, 3, 3, and 4, 4, 4. Okay, because it's broadcasting the column matrix. Okay, and I think this operates in the way that we would expect, right? So by default, even though this is one-dimensional, its shape is 3 comma, it'll get broadcast kind of across the rows. And but if I turn this into a column, so it's 3 comma 1 its shape, it'll get broadcast that way. Okay, here is D. And just so you know what A looks like, whoops. A is 1, 2, 3. If I do D plus A, it does exactly what we expect. Okay, it's going to broadcast it across the rows and do 2, 4, 6, 5, 7, 9. Here's C. Okay, C is 7 by 8, and again, I mean not 7 by 8. C is shape 2 comma, and D has shape 2 comma 3. Okay, if I do D plus C, it's going to complain. Okay, because it says here's the shape. The shape is 2 comma 3. D has shape 2 comma 3, and C has shape 2 comma. Okay, it can only kind of do the thing across the rows if it's one-dimensional. Okay. However, if I reshape this, if I reshape C to be shape 2 comma 1, okay, then it will be able to line them up. Okay, so I've got 2 comma 3, which is D, and it looks like this. It's 1, 2, 3, 4, 5, 6, and here's C, which is 7, 8. But if I reshape it so that it's kind of a column matrix, then it's happy to add 7 and 8. 7 and 8 and 7 and 8 here. Okay, is that okay? So it's able to do the 7, 8, 7, 8, 7, 8 across the values back here. Okay, 7 plus 8, 7 plus 8, 7 plus 8. So that's what we have there. Okay, these are. This is probably the weirdest part about broadcasting that takes the most getting used to. Okay, I've created E to be a column matrix. Okay, it's going to have shape 10 by 1, and F currently has just a shape of 11. Okay, going from 0 to 10. Okay, has a shape of 11 comma. But you can technically broadcast these together. Okay, what it's going to do is it's going to broadcast E into a matrix that's compatible with F, and F will get broadcast into a matrix that's compatible with E. So E will get broadcast into a 10 by 11 matrix, and F will also get broadcast into a 10 by 11 matrix. Okay, and so you can do this column plus this one-dimensional array, and it's going to take basically 0 through 9 and add 0 to all of this, to that column, and it's going to add 1 to all of that, and it's going to add 10 all the way across here. So it converts E into E and F. It looks at their dimensions, and it broadcasts E into a matrix and broadcasts F into a matrix, and then it combines the two. It's a little bit like the outer function in R, but also a little, there's some subtle differences, okay? Similarly, you can do like a multiplication thing, and now you've got a times table for, I don't know, did you have to make this in 3rd grade or something to learn your multiplication table? I don't know, when do you learn multiplication? Something, right? And then, so anyway, Python can do it very easily. Yes?
So is it only like the one-dimensional arrays that you can do, like where it'll make the matrix?
So I think, let me think. I want to say, yeah, it'll take column matrices that are like n by 1 or n comma or 1 by n, okay? And it can broadcast. I'm trying to think, can I broadcast? So what do I have? I have got D is here. Can I do, and D transpose would be this. I don't think I can match these two together, okay? Yeah, it's gonna say you can't broadcast like a 2 by 3 and a 3 by 2. Because I wouldn't, like, if somebody told me to combine these two, like on paper, I don't think I can do it, right? But if I reshape D, so if I do D reshape to be I have to specify it as a tuple. Okay, so reshape D to be 6 by 1, and then I do D reshape to be 1 by 6. Okay, then I can do that. Okay, so 6 by 1 will be the column, and 1 by 6 will go the other way, and you can. So these shapes are compatible, and again, it just takes each one and it figures out what's the required matrix that's going to be compatible. So it's generally you're taking column matrices or row matrices, or a one-dimensional, which is going to be treated like a row, okay, and it's going to broadcast. It'll turn them into an appropriate sized matrix and combine the two to kind of do these element-wise addition or multiplication things. I don't know if that helps. Okay. Oh man, we're out of time again. Okay, I had like so much more. Okay, I guess we're gonna have to pick up on this on Friday, and then and we'll go from there. Okay.